Hey students, welcome back to another lesson in physics. It's good to have you here. Glad that you're here. Again, what we're going to learn about today is a little bit of math, the math that is used in physics, and some of that math that you'll use. Some of you are familiar with it. It's going to be a little bit of algebra, some geometry. You might be in geometry now. Even some of the geometry you've had in the past will suffice. Some of you have had algebra or taking algebra now, you'll be fine there. And I'll need to review a little bit with you some trigonometry that you might have learned in the past or might be new to you, some a little bit of understanding how these relationships in 90-degree and right triangles. A higher level of physics course, say if you take a AP physics or if you take calculus-based physics in college, actually is a little bit easier, but you have to have some calculus. You actually do less math when you use the calculus. The calculus was actually invented by Sir Isaac Newton when he was 26 years old. He wanted to solve a problem. The problem was, why did the orbits of the planets, why are they like an ellipse, a cone? Why are they more shaped like a cone rather than a circle? So he actually went back, and his friend challenged him to that question, and then Sir Isaac Newton came back with the answer, and it was calculus. And so one day when you take calculus, or if, you'll be able to kind of understand where that came from. But for now, the math we'll be using in this class is going to be trigonometry and geometry with with some algebra as well. All right, so what we're going to do here is we're going to go ahead and work through some of the things that physics deals with. Because physics deals with really large things and really small numbers, it deals with all of these different types of numbers. Something, say the mass of a lead atom is 0.000000, all those zeros, 34 grams. So it's a very, very small quantity. So something as small as a subatomic particle of an atom all the way to something as large as a galaxy. An Andromeda galaxy is 2.5 million light years. A light year is a distance, and that is 25 with all of these zeros behind it, kilometers big. So these numbers are really difficult to write. If you think about it, imagine writing all the zeros, your eyes kind of glaze over. How many zeros am I supposed to write here? And they're difficult to calculate too. So there's more of a convenient way to write calculations that when we deal with things as small as an atom or something as large as a galaxy. And that's called scientific notation. And what scientific notation is, it allows you to put things like in a backpack, just like you might pack up all your binders in a nice backpack. You put your phone or your lunch or your water bottle in different compartments, and it's a convenient way for you to pack that. And when you get somewhere, you unpack it, right? Or you can think of it another way, like a transformer. Inside a car, the car transforms into Bumblebee. All right, so you can think of it as you unpack the transformer, becomes that super robot there, and then it turns into a car. So that's really what scientific notation is, transforming a number. It's still the same value. You're just expressing it differently. You're making it a little bit more compact. So in that last example, this lead atom right here with all these zeros will be expressed as 3.4 times 10 to the negative 34. And what's that saying is that it's 3,4 with all of these zeros in front of it. It's a very small number. So the negative says it's a very small number. The distance of Andromeda, that really large number, 25 with all those zeros behind it, would be 2.5 times 10 to the 19th kilometers. So when it has a positive exponent here, it's a very large number. And when you have a negative exponent, it's a very small number. So I'm going to show you how that works in a moment here. So I'm going to get just an ability to get out a little pen here for us so you can see some of this. So let me scoot some of this around here. Scoot my face over to here. There we go. All right. So when you have some rules about scientific notation, how do I even scientific notation? So the scientific notation is when you move the decimal so that one non-zero digit number is on the left of the decimal. That means basically your numbers are going to be between 1 and 9. Okay, 1 and 9, okay? The exponent of 10 will there be the number of places the decimal is moved. So when you move the decimal place, you count how many places you move that decimal. So any decimals that move to the left is a positive exponent, a large number. Anyone moved to the left to the right is a negative exponent. So for example, when what we did is we moved this 0, we counted how many times we moved the decimal point all the way to make this number somewhere between 1 and 9. So the number that would be between 1 and 9 and include both digits would be 3.4. So we're going to move our decimal point and count how many times we move it to 3.4. The same thing with this. So since we moved it to the right, that's going to be a negative exponent. Here, right here, the decimal point's right down here. We're going to count how many times we would move the decimal point to make this number 25 a number between 1 and 9, and that would be 2.5. So that's why this is 3.4 times 10 to the negative 34, which means we moved our decimal 34 places to the right. And then on this one, 2.5 times 10 to the 19th means we moved our decimal point 19 places to the left. Okay, so those are our three rules. It's always between 1 and 9. We count the number of times we move the decimal point, and that is what the exponent is. If it's moved to the left, it's a positive exponent. If it's moved to the right, it's a negative exponent. All right, so we can work on something here. Let's try this one here. Let's express 13,700,000,000 in scientific notation. So our first thing we would do. So let me get my pen out here, and I'll do this with you guys. Excuse me, I'm just kind of moving things around here. There we go. Okay. All right, here we go. Move some things around here. There we go. Now I got the pen working okay. All right. So we'll get our little thing up here. So what we do is we get our pen. We're going to count how many times we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to make this a number between 1 and 9. So that's going to be 1.37 times 10. How many did I move? I forgot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times 10 to the 10. Okay, that'll be times 10 to the 10. So that's what our scientific notation would be. This would be 1.37 times 10 to the 10 because we moved it 10 times. Okay, so another one here. We have another number. So we'll get this up, and then we'll get our pen out. Let me clear all my last ones there. So this time we're going to go. Let me get a little bit of a thinner pen. Might be a little bit neater. There we go. Make it a little bit thinner pen. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we move this 74. So this is going to be 7.4 times 10 to the negative 17 because it's a very small number moving to the right. Okay, so that's what that would be. And if we 10 to the negative 17, so we moved it to the left. Okay, so you can try a few of these on your own. I have assigned some homework for you, some to practice for that. You can practice on those. Okay, so the next concept we're going to learn right now is we're going to learn how what it means to have exact numbers and defined numbers. So this idea of significant figures. So the numbers that we use in math class, that you'll use in math class, Mr. Pierce's math class, or your other math teacher's math class, are exact numbers. But the numbers you're likely do in physics or in physics problems are measured numbers. Okay, that we're not exactly sure what the exact value is. Measured numbers cannot be exact. So they have to be estimated with some specificity. All right. So in the case of measure numbers, we only read the measuring to the number that our measuring instrument can handle. or the number of subdivisions. So for right here, this little scale, we only can measure down to 0.00. All right, that's the lowest we can go. The most we can report our numbers to is 2 decimal places. So we can weigh something, we can measure the mass of something of 12.72 grams. We can go 2 decimal places, but we can't go to the third decimal place without estimating. All right, so our scale is only accurate and only can report precision down to the hundredths place. Okay, so for instance, right here, if we were to look at this, we would see that we have a centimeter scale. Okay, and because we have divisions, the smaller numbers here are millimeters. So we have 10 millimeters in between each of our centimeters here, and this would be 5 millimeters. So this is halfway in between. So this would be 1.5 millimeters, but we can measure in between. We can estimate up to halfway in between, right where my dot is going. So we could measure this potentially as 1.50. We can actually go to the third decimal place because we were able to estimate in between. Our last digit would be estimated. So the measurement of this one would be 1.50 centimeters. Here are the significant figures. We go to 1, then we have 1.1. 1.2, and we're somewhere in between 1.2 and 1.3. So we could potentially say this would be 1.12, 1.25, 1.26. You see that we'd estimate, so that last digit would be estimated because we're not sure how far between 1.2 and 1.23 that is. So our last digit would be estimated. The next one here, we have a 1 centimeter, looks at lands right on there, and we can estimate to 1.0. 1.0, we know that it lands right there. And then our last one here, we see that we go out to 1 centimeter, go out to 1.1, not all the way to 1.2, so maybe 1.15 we could estimate down to there. So this instrument is able, this centimeter scale, this ruler that we have, we're able to estimate down to a certain amount. So our last digit is estimated. So here's some rules about significant figures. In significant figures, all non-zero numbers, any number that's not a zero, is considered to be significant. All zeros between non-zero numbers, so something like 107, 107, the zero there is significant. And then all beginning zeros are not significant. I'll give you some examples of this in a minute. And then ending zeros are significant. This is the crazy one. Listen up here. All ending zeros are significant if the decimal point is written, but not significant if the decimal point is understood or it's not there. Okay, so here's some examples here. All non-zero digits are significant. So we have the number 543. It's going to have 1, 2, 3 significant figures because there are 3 non-zero numbers there. Okay. The number 22.437 has no non-zero numbers, so it has 5 significant figures because that's 5 digits. The number 1.321754 has 7 significant figures because there's no zero. So when there's no zeros in there, you just call them all out, and that's how far you can report. So in this number, you can report all the way to this decimal place. But this one, you can report to that third decimal place. Okay. Now, the second rule is all zeros between non-zero digits are significant. So something like 7,004. These two zeros because between a 7 and a 4, which are non-zero numbers, they're significant. So that means that they count. They're 4 significant digits here. Okay. Here we have 10.3002. That has 6 significant figures, but because we have a 0 between two non-zero numbers, so it's 1, 2, 3, and then we got these 2 zeros, and they're between the 3 and the 2, so we count all these up as 6. Okay, and then finally, what we have is two more here. We says all beginning zeros are not significant. So all these zeros in front of here, you have zeros in front of all these numbers, the only significant figures are the non-zero numbers. So if you have numbers to the left of non-zero numbers like that, those don't count. Okay, this only has two significant figures, all right? This one right here is 0.02, only has one significant figures because all the zeros start or to the left of your non-zero number. Now this one right here, these zeros won't count because they're in front, they're to the left, or they're in the beginning. But these zeros right here will count because they're in between these two threes, which are non-zeros, okay? So you kind of, maybe I'll be picking up that the kind of the tricky part of significant figures is gonna be, what do I do with my zeros? So anything to the left of my non-zero numbers don't count. But if they're in between, they're considered placeholders and they are significant. Now, what to do with ending zeros? The rule is, if there is a decimal point that is there, it's actually written down or typed in there, then all the zeros behind it count. So 37.300, these are called trailing zeros, they'll count. So these count, all 5 of these numbers count. Same thing with 33.00000, because the decimal point is there, anything to the right is going to count. Okay. Now 100 with a point there, that means you're telling me that you know to a fact to this, you're estimating this last digit. So we have 3 significant figures here, all right? Let me see, I gotta move this thing out of my way. It won't allow me. Okay, and then if there's not a zero, let's say there's not a zero right there, this would only have one significant figure. So if you see that 100 there, 100 without the significant figure, without the decimal, excuse me, if the decimal is not there, it has one significant figure. So 100 point has 3, and 100 without a decimal point just has 1. Okay, so what we're going to do here is I've assigned you some scientific notation help to help you work through this and some significant figures. So look on Google Classroom for that. So thanks for your attention. Work on this as best you can because this will be an important concept for the rest of the year. Okay, see you soon. Bye-bye.